Okay, so coming to the mutual coupling between two antennas. Okay, so this is another major application of CEM. Right? So what have we just sort of let's look at what we have done so far. So we had one antenna like this. Let's call it antenna A. Okay, and what was this antenna A doing? It was radiating a field in free space. So, and the input impedance that I calculated was assuming, I mean, what are the boundary conditions that we applied over here? To solve this problem, what was the boundary condition? We said that EZI R plus EZ scattered at R is going to be equal to what? 0, right? For R belonging to A in the conductor, it is a perfect conductor, the total field is 0, right. Now, what happens if there is some other object in the vicinity of this antenna? That object will also have some current induced, I mean the field will fall on it, induce some current, that induced current in turn will radiate another field, that field will come and fall on this antenna. So, this boundary condition will not be strictly true because there are more fields over here. If this boundary condition is not true, my solution changes, right, that means my current distribution changes. If my current distribution changes, what happens to my impedance? It will change, right. So, the input impedance that you have calculated for a single antenna in free space, you are very happy about it, you put it into an electromagnetic environment where there are various objects and suddenly you find that your performance is not so good, right. So, one major reason for that would be there is since the environment around has changed, the input impedance of the antenna has changed, therefore, the matching condition is no longer valid. So, how do you calculate this? So, again there is a vast theory of approximate methods, but again in CEM what we will try to do is give you an exact way of calculating this. There is more, it is more work, but it is more rigorous than the other case. So, what we will do is now we will add another antenna element over here. Okay. So, let us say there is one antenna radiating and I have introduced one more antenna in its vicinity. Okay. So, another antenna comes in over here, we will call it antenna B. Okay. This antenna can be active or passive. So, what is that? What does active antenna mean? That it is also radiating, that means it also has a generator. Passive antenna could be, is just sort of in receiving mode, or like one of these Yagi-Uda antennas, there is one driving element and there are various rods behind it which are there, right. So, that is an example of a passive element. So, this situation is general over here. So, how does this, what will happen physically is this guy radiates a field, a current is induced on it, right, and then that in turn will radiate another field. Okay. So, there are two ways of thinking about it. One way is that like a series. A sends something to B, B induces, B radiates, sends to A, this changes the current in A and so on back and forth, right. It will not continue forever, there will be some steady state solution to this. Okay. So, in the steady state there is going to be some current in A and some current in B, right. So, how will this boundary condition get modified? Then, if I ask you what are the fields at any point on A, so you will have EZI, okay, that is always there, that is the voltage, I mean the field produced by the voltage source. Then you have the self field, right. So far this is what I had in the single antenna case. Now, right, so now there is going to be a plus EZ, S for scattered, right. So, the field scattered by antenna B, right. So, this was single antenna and this is both antennas. So, in terms of a circuit model, how can I think of this? So, actually a very simple 2-port network also drives home this picture very well, right. Remember, in our earlier case I had the generator and one load connected across it, right. Now that situation is changed a little bit. I have something like this. So V1 and I1 goes in over here, V2 and I2 appear over here, right. So this is, I mean, for electrical engineers this is very standard. So I can write V1 is equal to Z11 I1, Z12 I2, and V2 is going to be Z21 I1 plus Z22 I2. So what are these Z11 and Z22? These will be called the self impedance, right. So these are the impedances in the absence of the other antennas. This is what we had so far. When there was a single antenna, nothing else to disturb it. And then Z21, Z12, these are called the mutual impedances. From a circuit, from an antenna or a circuit designer's point of view, what is the impedance that he or she needs to match? Is it Z11, Z22 or what? It's neither Z11 nor Z12. Z in, right? So that is V1 by I1. At port 1, that is the impedance, right. So that is going to be Z1D, I will tell you what D stands for, and that is going to be equal to Z11 plus Z12 I2 by I1, and this Z1T is called the driving point impedance. Similarly, V2 by I2 will be the Z2D, which will be Z21 I1 by I2 plus Z22. Okay. So you can see that the driving point impedance depends on knowing I1 and I2. I need to know what these currents are, only then I can find out what is the matching network to design, right. So again, how do we calculate this? So again, this method, which is called the induced EMF method, and various other methods, they are used to approximate. If I can get an approximation of the current distribution, then I can calculate this driving point impedance and all of that, right. And that works for very special cases of, you know, parallel conductors, only Z directed and so on. But if you have some general configuration, it is it's not accurate. So CEM again allows us to calculate these exactly. Okay. So is the setup is clear? When I have two antennas in the presence of each other, there is going to be you know, some current IA over here and some current IB over here. And these are steady state currents after all the multiple reflections have happened. And our objective is that in the presence of IA, I mean in the presence of the other antenna, tell me what is Z1D, tell me what is Z2D. Okay. So let us proceed. So the boundary conditions that we have, let's redraw this antenna over here. So this is antenna A. Okay. For simplicity, what I am going to do is the antenna B, I am just going to make it passive, okay, but I can easily add a generator to it. Okay. So this is my antenna B, and there is IA here, IB over here, okay, some distance D apart. Now, since this is the very first introduction of CEM to mutual coupling, I need to make some simplifying assumptions, which is not required, but just to keep the derivation simple. So the assumptions I will make are both are z directed. So, both currents are z directed and radius is much smaller than wavelength. Okay. So, this just allows the math to become a little bit easier. Is that okay? So, with a single antenna, we will keep comparing with the single antenna case and build the theory of two antennas to each other. With the single antennas, our boundary condition was Ez Ia. So, Ia is incident field for an element A R plus Ez SA R is equal to 0 for R belonging to A. Okay. And now we are going to, for two antennas, I need to find out the boundary conditions. So, very simply they will be, so let us take two cases, R belongs to A and R belongs to B. Okay. So, the first case, what will I write? Ez IAR plus Ez, this is the self field and some field, scattered field due to B being measured on A. This must be equal to 0, right? Okay. Second boundary condition, what will be the first term? So, there is going to be Ez scattered from A, right? Let us write it in a in this way. So, this is the field that is produced due to current in A falling, producing a field and that field falling on B, and Ez S B R is equal to 0, okay, for R belonging to B. So, we assumed B has no source. If it has a source, there will be a Ez IB, that is all. Okay. Very simple to deal with. Okay. These two conditions, there is a name for them, they are called null boundary conditions. So, let us remind ourselves how we solved the single antenna problem.
So,
yeah.
Why you get an incident field for B?
No, I am just assuming. If there was, there will be one more term. We will add it, right? There is absolutely no difficulty. We can add like this term over here, right? A similar term Ez IBR will be added to the left hand side of this. Oh, so, I have some voltage source in A which is generating a field, and that is the first term. The second term is the field due to the current flowing in the antenna itself, and the second term is the field due to the current in antenna B, right. Now, and this is true for any point on the antenna A. When I move to antenna B, the same logic holds. So, if there were a source in antenna B, then I have to add the source term, that is all. Is it clear? So, let me write it here, else add Ez IBR to LHS, so that there is no confusion. Okay. So, let us remind ourselves, how did we solve single antenna? It was the Pocklington's integral equation, right? Pocklington's integral equation, and let me just write it down over here. So, minus LA by 2 to LA by 2. So, there was a IA Z prime, then I had d2 by dz2 plus k squared acting on Green's function, which was a function of zz prime, right, and I had a dz prime, and this whole thing was equal to by boundary conditions, this was equal to minus E z incident at z. Right? This was our very simple thing. Now, this character over here is going to appear many times. So, I am going to make a shorthand notation for it. So, this term over here, I am going to call it j omega epsilon naught times k z z prime. Okay, just a shorthand notation for this term. So, what happens now? Well, maybe I should write it over here. So, this will become integral from minus LA by 2 to LA by 2, then IA z prime k z z prime dz prime is equal to minus E I z z. Just a more compact way of writing the same equation. And here what was my G had what kind of terms? It was e to the minus j k r by 4 pi r, and r was of the form square root of a square plus z minus z prime squared. We have already seen this before, right? So, it is a function of z and z prime. Now, we go to the case of the integral equations for two elements, right.